Double identity for Di-logarithm function. So basically in this video we will try to prove this identity of Di-logarithms, and some of you might call Di-logarithm as also Spencer's function. Yeah, and this is just a special case of polylogarithm function, and polylogarithm function is LS of g where s is 2. Now let's try to prove this. So basically we will go from the definition of polylogarithm function. Polylogarithm function is defined as sum going from n equals to 1 to infinity of n to the power, if this is g, n to the power g by g to the power n, g to the power n by n to the power s. This is the definition of polylogarithm function with base s and the input g. Okay, so now our s is 2, so this will be g to the power n by n square. Yeah, so now let's solve this. Basically the first thing over here is just sum for n going from 1 to infinity, g to the power n by n square. The second is sum going from n equals to 1 to infinity minus g to the power n by n square. Now over here, like how do we deal with the minus 1 to the power n? So basically now I can write this as sum from n equals to 1 to infinity. Our denominator is same, n square, and over here we have g to the power n plus minus 1 to the power n and g to the power n. Yeah, so now what we can observe is, like, when n is even, this will be g to the power n plus minus 1 to the power even is just 1 g to the power n. This will be 2 times g to the power n. Yeah, and over here, okay, 2 times g to the power n when n is even. So that means 2 times g to the power some even number. Yeah, okay. Now when n is, okay, okay, so here's some mistake. Okay, basically not 2 is not in the bracket, basically 2 times and then g to the power some even number. Yeah, now when n is odd, we will have g to the power n where n is odd minus this minus 1 to the power on odd is minus g to the power n. So this is 0. So basically from here what we can say is, so basically now we can let the sum go from n equals to 1 to infinity, and at odd this cancels out, so only we have the even terms. So g to the power 2n plus g to the power 2n by 2n whole square. Yeah. And so this is sum from n equals to 1 to infinity 2 times g to the power 2n by, this is 4 times n square. Yeah, so that's why this is 1 by 2 times sum from n equals to 1 to infinity of g square to the power n by n square. Now from the definition of the Di-logarithm function, now this is just li, our power is 2 and our input is g square. Yeah, this is just 1 by 2 li2 of g square, and that is what we had to prove. Now in place of Di-logarithm, if we had any polylogarithm function, for that case you can go through a similar proof, and you can derive that this is actually equals to 2 to the power 1 minus s and then polylogarithm function of g square. Yeah, and this is the special case where you put s equals to 2, so we have 2 to the power 1 minus 2 to the power minus 1, which is 1 by 2. And yeah, this is how you prove this identity. So basically just invoke the sum definition, and notice that minus 1 to the power n goes to minus 1 and 1 for different cases, and when even we can add them. So this was the proof. Hope you enjoyed the proof. Thanks for watching, and look forward to seeing you in the upcoming videos too. In this playlist of Di-logarithm we have other videos which explain other properties too, such as the Euler's reflection formula, yeah, or inversion formula, or Landon's identity. Yeah, so basically I have also proved those. Yeah, so Yeah, thanks for watching.